Now that we've defined the impulse imparted to an object by a force acting on that object over time, we can combine that idea with Newton's second law to derive the impulse momentum theorem. So the net impulse acting on an object over some time interval would be the sum of the impulses imparted to the object by each of the forces acting on the object over that time interval. So it would be the impulse imparted by force 1 plus the impulse imparted by force 2, and so on. And since integrating is just adding, we can represent the sum of the integrals as the integral of the sum of the integrands, as long as these are each over the same time interval. So this is the net force right here, and so I'm arguing that the net impulse is the result of integrating the net force over time. And by a similar argument to the one we made here, we can say that our net impulse must be in the same direction as the average net force. Net impulse points in the same direction as the average net force, and by Newton's second law, your average net force points in the same direction as the average acceleration. So hence, these three vectors are always parallel to each other. Average net force over some time interval, average acceleration over that time interval, and the net impulse imparted to the object over that time interval. Okay, I'm going to rearrange this equation a bit. Okay, the net force appearing here in the integrand also appears in Newton's second law, so I can replace the net force with mass times acceleration. So I put mass times acceleration in here. Acceleration is the time derivative of velocity, so dv dt. So m times dv dt equals our net force. So I've replaced the net force with m times dv dt. And then here we can cancel the dt's. And by doing so, we've changed our independent variable. Now instead of time being our independent variable, the d thing is dv. Our velocity is now our independent variable. So since our independent variable is no longer time, we have to update our limits of integration. Since we changed from time to velocity, then our upper and lower limits have to be replaced with the corresponding initial and final values of the new independent variable, velocity. So instead of going from time 1 to time 2, we're now going from velocity 1 to velocity 2, where of course this is the velocity at time 1 and this is the velocity at time 2. Mass is just a constant, so we can factor that out of the integral. It's just going to sit out front here, and we're going to sum up all the changes in velocity. So of course, summing up all the changes in velocity, that's going to get us summing up all these infinitesimal changes in velocity, it's going to give us the finite change in velocity, the delta v, v final minus v initial, final velocity minus initial velocity. So that gets us here. If I distribute that mass across those two terms, we get the net impulse equals mass times velocity 2 minus mass times velocity 1. So apparently the net impulse is equal to the difference in the quantity mass times velocity. This is final value of mass times velocity. This is initial value of mass times velocity. We've assumed here that mass was constant, so we pulled it out. We're going to rename this quantity, mass times velocity, we're going to call P, and give it the name momentum. So this is P2, the final value of mass times velocity, minus P1, the initial value of mass times velocity, or delta P, the change in momentum. And here we've got the statement of the impulse momentum theorem. We've argued that the net impulse acting on an object from time 1 to time 2, which is the time integral of the net force acting on the object from time 1 to time 2, that is equal to the change in this quantity, mass of the object times the velocity of the object. We're calling this quantity momentum. So the impulse momentum theorem says that the impulse on the object equals the change in momentum the change in momentum of the object over that time interval. Another way to put it in words is to say that a net force acting over time changes the momentum of the object it's acting on. So looking at this equation here, I've got net impulse equals change in momentum, impulse momentum theorem here. Net impulse equals change in momentum. To my eyes, that kind of looks like an E, J, and an O and a P, as in E, J, O, P, as in Eric Johnson is overpowered.